This is Lab 3, Black Hole and Orbits. Introduction. This lab is split into two parts. Both parts of this lab focus on using F-grav of objects in space to find other values based on the orbits of the objects in the models. Part 1 focuses on finding the mass of a black hole based on the orbit of a star using the force of gravity on the star by the black hole. Part 1 found that the mass of the black hole was around 1.25 e to the 34 kilograms. Part 2 focuses on finding the initial velocity needed by a spaceship to orbit both the moon and the planet without crashing. Part 2 found that the initial velocity needed for the spaceship to orbit both was 2.45 e to the 4th, 2.45 e to the 4th, and 0 meters per second. This lab has no errors, as any errors in the models would have caused failure or not given a good estimate. Principles used in lab. Principles used in this lab are velocity, momentum, change of velocity, change of momentum, the gravitational constant, F net, which is equal to change in momentum over change in time, F net parallel, F net perpendicular, and F grav equals G times M over R squared. Part 1, Black Hole. This model is focused on finding the mass of a black hole based on the orbit of a star around the black hole. As the star orbits the black hole, the model takes in the values from the orbit to calculate the mass of the black hole at that point in time. The estimated mass of the black hole changes over time and needs to be averaged in order to find the closest value to the true mass of the black hole. This average estimation of the mass of the black hole was 1.25 e to the 34 kilograms. Computational model black hole. This code takes values from the star's mass and orbit in order to calculate the mass of the black hole. It starts by calculating the change in velocity, change in momentum, and F net, which are later used to calculate values needed for the model. At the end, it calculates the mass of the black hole and prints it for the user to see. Model black hole. This is the model of the star's orbit around the black hole. The numbers at the bottom of the image are the estimated masses of the black hole. The sun is the yellow sphere, the black hole is the black sphere, the star's orbit is the green line, and it moves counterclockwise, and the arrows F net, F parallel, and F perpendicular are also coming from the sun. Part 2, Orbit and Don't Crash. This model was focused on finding the initial velocity required for the spaceship to launch off the moon and orbit both the moon and the planet without crashing into either. The model calculated the orbits of the moon and spaceship based on the force of gravity between all three objects and their distances from one another throughout the model. The point was for the user to input values for the initial velocity of the spaceship until they found a value that completed the orbiting goals within the time limit of the model. I found the initial gravity of 2.45 e to the 4th in both the x and y component in meters per second allowed the spaceship to orbit both the planet and the moon without crash. Computational model orbits. This code takes in the user's guess for the initial velocity of the spaceship, lines 52 to 57, and then calculates the F-grav and distances between the planet, moon, and ship. It uses the F-grav and distances to calculate the F-net on the ship and the F-net on the moon, which are used along with the velocities to calculate the orbits of the moon and spaceship. The code has an error case that is not shown that says if the spaceship has crashed, the initial velocity was not right. Model orbits. This is the model of the orbits of both the spaceship, which is magenta, and the moon, which is in cyan. The lines below the model tell the moon's orbital speed and orbital period. Also, they state when the max time has been reached, meaning that the initial velocity passed the test and the spaceship did not crash, as there is not a message about it crashing. What if? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. F net and the rate of change of momentum are equal, but different from each other. F net is the forces acting on the object, and the rate of change of momentum is the movement of the object caused by the forces. F net par and dp par differ in that the F net par is the magnitude of momentum and dp par is how fast the speed is increasing or decreasing. F net perp and dp perp differ in that F net perp changes the direction of the momentum and dp perp is the rate of that momentum changing direction. What does it mean? This imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? The computational model would need to find the distance and forces of gravity between all four objects. It would also require their velocities. Then it can calculate the orbits of the objects based on these things. The black hole would have a dominant interaction on all the objects in the system because it has the largest mass and won't move. So the main interaction would be the planet on the moon, the star on the planet, and the black hole and the star because of the distance between the objects.